So this is part 3 of pi theorem. In part 1, we learned about physical models and how pi theorem can help you to design and report your experiment by identifying pi terms. In part 2, we learned how to after we identify the pertinent variables, how to come up actually, like use a systematic method to come up with pi terms. So what? Like, why do we need these pi terms other than designing the experiment and reporting the results? We need these pi term for another additional application, which is to scale from our physical model to our prototype. That's why that's like another application, like a third application, like designing experiment, reporting the experiment result. But equally important is to scale back from and forth, yeah, from the model to the prototype and from the prototype to the model. And we will do an example. So basically, here we will apply the principle of similarity in dimensional analysis, practice physical modeling on non-dimensional parameters, and use non-dimensional parameter by term to predict the prototype performance from the model performance. So this is more like a recap. Like we did this already, like we applied the principle of similarity. We came with the non-dimensional parameters. In this video, we will specifically look at how to use non-dimensional parameters like this PyTerm to predict the prototype performance from the model performance. Okay. So when similarity is achieved, again, geometric similarity, kinematic similarities that has to do with velocity and time, and dynamic similarities that has to do with forces. Yeah, we can predict the prototype performance from the model performance. So that's the whole idea. Uh, because why is this? Because when we ensure similarity, the dimensionless parameter, yeah, that's the key idea. Like when we ensure similarity between the model and the prototype, then the dimensionless parameters, like these pi term derived from the governing equations, yeah, these are identical for both systems, for the model and the prototype. That's the whole idea. Like if these two things are similar, we drive this by dimensional parameters. This by dimensional parameters will be similar, yeah, for your model and your system. And when all independent terms match, like all these independent pi terms match, the dependent term will also match. Like when all your independent variables match, your dependent variables will also match. And this will allow the prediction from the model and apply this prediction to the prototype. Because all my independent variables match between the model and my prototype. Similarly, the dependent variable, like the quantities that I'm interested in, my state variable, what I'm interested in predicting, which is in that case the drag force, for example, or whatever, yeah. Or like I will show you another example, like would be the drop in pressure, yeah. So the drop in head, like in hydraulic head, or any like something related to structure analysis, yeah, shear stress or whatever, yeah, will match. Okay, so let's I mean let's look at our like how to mathematically represent this. Yeah, so here like we can mathematically represent this a little bit bigger. Like let's say I have pi1, which could be like let's say my independent variable. Yeah, my dependent variable. That's like a function of like pi2. Yeah. Just as we saw in the previous example, like pi1, that was like the drag force plus some other term. That was a function of like Reynolds number. But it could be, remember, because we only had the 5 parameter, we could have 6, 7, 8 parameters, so we could have more than one pi terms, yeah? So that's like it's a function of pi 2 all the way to pi, and you can have as many of them as you want, yeah? So these are, remember, these are like dimensionless, yeah? So if, okay, if pi 1, or let's call it like pi I, yeah, of the model, yeah, is equal to all the pi I of the prototype, yeah, for any I, like for I from 1 to n, yeah. So I, that's like from 1 to, from 1 to n, yeah. Okay. Then, like if, then I want, like, model will, pi 1 model will be equal to pi 1 prototype. So that's basically the mathematical rule. Like so, I1 would be, so if, sorry, this here, sorry, I messed up here. Let me just write it like in better detail. Like so, I here, that would be from 2, 3, whatever, yeah, 2. Okay, so that's the idea. So if all my dependent like variable, like the pi of my dependent variable between the model and the prototype match, so this from 2, like this would be like here, like that's like the renal number, whatever, like all these other uh, uh, pi terms that represent like the independent variable, and here pi 1 which represents the dependent variable, which is like the drag force or drag coefficient, as in this guy here. Then, so if all my independent pi term of the independent variable matches, then the pi term of my dependent variable, oops, that is for my dependent variable will match. So basically, that is the rule. Yeah. Okay. So let's look at an example like. So in other words, like if all the independent pi terms between the model and prototype are identical, then the dependent term will be identical. All independent terms are identical. The dependent term pi will be identical. So let's look here at an example. Yeah. So let's look at this example. So dimensional analysis provides like scaling law to predict prototype performance from the model performance. So let's say we have again like this car. Okay, so that's like our prototype. So here this is our P prototype and this is our M, our physical model. Yeah. So like this is like the length of the prototype. This is we want again to estimate like the drag force of the prototype, velocity. So the drag force will be a function of velocity of the prototype, uh, uh, air density, and air viscosity in that case. Yeah. And similarly would be for the model. Yeah. So here we have like a small scale model of our prototype. So let's read this problem. So an aerodynamic drag. So here we want to estimate like the drag of the aerodynamic drag of a car need to be determined at speed of 35 uh, uh, mile per hour at an air temperature of 20 degree centigrade. Yeah. The tunnel wall are far enough. So we put this like in a wind tunnel, like we created like a small, like a a small physical model, like with a smaller scale than the prototype, and then the tunnel wall are far enough to interface with the drag force of the car. So we have like a big wind tunnel, and which the wall of the tunnel will not interfere with the car. So the engineer built a one-fourth scale model of the car with the same geometry to test it to test in a wind tunnel at a temperature of 0. So let's write some numbers here. Okay, so let's fill this table with some number. So for the aerodynamic drag of a car need to be the dynamic at an air temperature. So this is like the prototype. I have like the temperature is 20 degree. And the model, like my wind tunnel, the temperature there is like 0 degree. Yeah, so temperature at the atmospheric pressure. Both are at the atmospheric pressure. Yeah, okay. At the same geometry. So the D, the length here, uh, that would be 1. Like that would be like, that's like 4 times larger than this one. So the length here, that would be 4. And the length here, that would be 1. Yeah. And again, like here, I'm not expressing lengths in meter or feet or anything. Why? Because it doesn't matter, because like I'm getting the ratio between these two. So regardless of the unit of this one and the unit of this one, as long as they have the same unit, it will cancel. So I'm not like putting anything here. Doesn't matter. Okay. Uh, so that is like the information that we have. Like we have like one force, we have like this is the temperature. The wind tunnel has a moving pill to simulate the ground under the car and to achieve kinematic similarity everywhere in the flow. So this wind tunnel has a moving pill to simulate basically velocity. Yeah. So velocity is simulating. Yeah, is simulated. Okay. So now the question is, ignore air compressibility, like ignore that the air get compressed. Determine how fast the engineer should run the wind tunnel to achieve similarity between the model and the prototype. Okay, so in order, so this is the geometric scaling. Now we want to see how much like velocity we need in the wind tunnel to scale with that velocity that's giving here. So the prototype velocity is like 35.0, and we want to see like what velocity do we need to put here to scale with this one giving this geometry. Yeah. So first so that's for that's the kinematic scaling. The dynamic scaling, we need to find basically the density of air. Yeah, here we have a bracket here. We need to find like the density of air and the viscosity of air at this temperature. Like how to find this? So the problem didn't give us like any density of air or viscosity of air. So how could we do this? Yeah. So we cannot solve the problem. Yeah. Yes or no? Well, I mean, you just Google them. Yeah. So basically, remember, like now you are graduate student, not all information need to be given to you. You need to, because I mean, you are now an engineer, you are not an undergraduate student. So like you do your job, you cannot say, oh, I'm not giving this, I don't know what to do. I mean, I cannot solve the problem. Just go and find them. So let's just write uh, uh, density of air at a different temperature. Yeah, let's do this one. Density of air at a different temperature. So let's go here. So like you see here, this is in Fahrenheit. Let's do it in Celsius. So here is in Celsius. And you see here, this is density. Yeah. And which one do we want to do? So we want to, let's go to our problem. So we want to find like the density at 0 and at 20. Yeah, so at 0, that's like this number here. Yeah, so we can copy this guy. Yeah, this would be at 0. We make it a little bit bigger. Uh, undo. Let's do this one here. Undo, doesn't matter. I can just increase the font. Yeah, so we can just press, oops, don't need this guy. We can just come here, make this a little bit bigger, maybe 36. Oh, that's too big. Okay, 26. Okay. So basically that is a density, and then we want it at what, 20 here. So we got like this guy here. We do this guy and we make it like 26. Yeah. Okay. So we here, oops, what did we do here? Need to move this guy here. Need to move this guy here. We need to, okay, here we go. So we got like the density, and let's see. Do we have so okay, so here we have the density, and what do we need? We need also the viscosity, yeah. So let's Google also this one. This is viscosity of air. Oops. At different temperature. As we go something here. So we got like the viscosity, that's in Fahrenheit, like that's in Celsius. And we need it in we need it at like let's say at this guy. Yes, we got like here we got like this guy here, 10 to the power. Let me just write this down. So that would be we can kind of at atmospheric temperature. So that's like the at atmospheric temperature. Yeah. So at 20, like 1.8, 1.7. Yeah, that's okay. 1.7 and 1.8 10 to the power. So here, that's like 1.7 e to the power minus 5, for example. Yeah, let me write it down. So here, that's like 1.7 e to the power minus 5. Oops. And here, that's like 1.8 10 to the power minus 5. So hopefully I got this correct. So at 0 that's 1.7, and at 20 that's 1.8. Yeah. So 1.7 and 1.8. Yeah. And again, it doesn't matter because they will cancel out. Okay. So basically, that is that's like we fill this one, and then I mean it's not asking about this now. So ignoring air temperature, wind tunnel achieve what is velocity like. So here we have the length, we have all these guys, yeah. We have the density, we have the viscosity, we have the velocity, and so we want to find this guy. So we have all these guys, and we want to find this guy. How can we do this? That's very simple because in order to do this, uh, let's maybe first let's write our pi term just to remember what we did last time. So remember, like last time we had like our pi 1 that is equal to like fd over rho v square d square, and then we have our pi2 that is rho vd over mu. Yeah. So let's see which one can we use here. Yeah. So obviously we use this one pi2 here, and now we know uh, because of similarity, yeah, because we have like a dynamic, we have geometric, dynamic, and dynamic similarity. We know that that pi 2 of the model basically is equal to pi 2 of the prototype. So it is that simple, yeah. So pi 2 of the model is equal to pi 2 of the prototype. So basically, like, I mean, if you just want to write it down, like rho model v model d model is equal to mu model. That is, it would be equal to rho prototype v prototype d prototype over u prototype. That's basically it. Yeah. So I mean, we have all this information. Yeah. So you have this guy, this guy, this guy, this guy. We only, oops, here. Sorry, I made a mistake here. That's prototype. Yeah. So basically, that is uh, you can basically like, I mean, you can arrange the terms. That might be like a good idea. It's not like a bad idea. So like, so you get each one like on let me show you. Like, so basically we are looking for the V model. Yeah. So V model, that would be equal to V prototype. And then what? Okay, so, and then that would be like rho prototype over rho model. Yeah. And what else? That would be D prototype over D model. What else? That would be mu model over mu prototype. Yeah, isn't that easy? Yeah. And can we fill, so we have here, so now you see here, it's really like, that's why I told you like the units are not really important, because all these are like, this is dimensionless, this guy is dimensionless, this guy is dimensionless. So the unit of this guy would be just the unit of this guy, because it is also dimensionless, which would be also dimensionless. Yeah. And that's why you see I have like in this, I have mile per hour, I have here meter per second, I have kilogram meter square, I have, doesn't matter. Yeah. So really it doesn't matter. Yeah. Uh, uh, so uh, so basically I will get here this guy, like the velocity of this one, uh, that would be I have this value here, like a little bit different, but anyway, I, I'll get the velocity, this one, that would be the velocity of the prototype, which is 35.0 times the rho of the prototype, that would be 1.204 over 1.9, yeah, something like this. Then I'll have the uh, of the prototype, that would be 4 over 1, and then I'll have this mu here. I have like in the answers that I have, like this mu is a little bit different. So like I have like, let me put the other mu that I have, so we get the same answer. So here, like I have for this one, I have like a little bit different, 1.8 to 10 to the power minus 5, and here I have 1.792 10 to the power minus 5, yeah, 9 to 10 to the power minus 5, yeah. So here I have, this is of the model, so that would be 1792 over 1.82, yeah. So if I did this calculation, then I got like 1.28, like 0.11, or meter per, or mile, actually not meter, just like mile per hour, yeah. Okay. So in order, oops, to achieve, remember here, so that's important, yeah. Okay. So remember, in order to achieve dynamic similarity, we need to achieve geometric similarity and kinematic similarity. Geometric similarity, we achieve them, but like by having the geometry of our proto model is similar to the geometry of the prototype. Kinematic similarity, we need to achieve it by making the velocity, like in this wind tunnel, like on the belt on the wind tunnel, like 128. So if we have like a velocity of 128 and the model that is like 1/4 of this guy, then like with this like geometry, we need this velocity, and then we will have we achieved basically, like that's how we can achieve a dynamic similarity. Okay, so now the question is, now like let's get to the question, like the second question here is, suppose that the engineer runs a wind tunnel at the calculated speed to achieve similarity between the model and the prototype. So uh, basically, like let's fill one more information here in our table. Where's our table here? So our table here, so we got like, what do we have here? We have like one, make it bigger, 28.11. Yeah. So now these two things has like, we achieve like kinematic similarity and geometric similarity, and then we should have like dynamic similarity. So suppose that the engineer runs a wind tunnel to calculate the speed to achieve similarity between the model and the prototype. Using the drag balance, and the measured aerodynamic drag force in the model car is pound force. So that is the drag force that we measured in the wind tunnel. Yeah, as I measured this using a drag balance. Predict the aerodynamic drag force of the prototype at these like velocity and this temperature. So can we do this? Yes, that is very easy, because here we have our like first pi term. Remember, like this is our first pi term here. We can write it down here again. Let me let me move this guy a little bit up. Let's move it a little bit up. delete this guy here and delete this guy here. Okay, like move this a little bit up. So here, from this one, we can calculate like the drag force from pi1. So pi1, basically that will be the force, the drag force over rho v square over L square. Yeah. And same thing as we did before, like pi1, because pi2, like the independent variable, because like since pi2 of the model is equal to pi2 of the prototype, therefore, therefore pi1 of the model is equal to pi1 of the prototype. Yeah. So here we get like pi1 of the model is equal to pi1 of the prototype. Yeah. Oh, this doesn't look good. Just write it in your line. Pi1 of the model is equal to pi1 of the prototype. And so basically that will like the pi1 like the force drag of the model is equal to rho model v square model L square like model, yeah, is equal to drag force of the prototype, rho prototype, oops, v square prototype, L prototype square. Yeah, that's so so here like we have new piece of information. So we have like the model here. This is what we measured, like 16.1, and we want to find this guy. Yeah, so that's very simple, because now here, look at this guy. Yeah, we have the model, that's like 16.1 or whatever. We have this let me just copy this table here. Let me just make a copy of the table. So here, copy the table here. So we can so let's look here. I mean, this is the one, like, let me delete this one. This is the one we want to calculate, yeah. So let me just delete the answer. So here, let's just do this, yeah. So we have the drag force of the model that is giving like 6, or even before we do this, like I would like, before we do this, let's just do what we did in the previous example, because like let's just arrange the terms. So like I will say like the drag force of like the prototype, like this is the one we are interested in. That's like the drag force of the model plus what time what time rho prototype over rho model. Yeah. So rho prototype over rho model time what time uh, did I do this correct? Okay, do this correct. Let me do. So like this guy is equal to this guy. So basically, uh, that would be like rho prototype over rho model here, and that would be v prototype over v model square, and that would be L prototype over L model square. That's what it should be. Yeah. So if you did this calculation here, yeah, well, that's this. If you did this like, oops, let me just do this. If you did this like, you just basically substitute these value. So if you substitute it here, like 16.1 time raw prototype, which is what's this one? 1.004 divided by 1.292 over V prototype, which is the velocity of the prototype. That's like 35 over 128.11 square. Yeah, delete this guy here. Square. The lens prototype over lens model, that's like 4 over 1 like a square. Yeah. So if you did this calculation, so when I did this, I got 17.9. Let me check it. Let me check this number so we can. Let's just do open Excel. Let's do it with Excel. Yeah. So let's just do the calculations with Excel. So here I have 16.1. That's like 16.1 time 1.024 divided by 1.292. Yeah. Okay. This is time 35 divided by 128.11 like square time 16. Like 4 squares, that's 16. I did this, then like the numbers that I got like is, I don't know if you can see it here. That's what I got. 17.9. Yeah, so I got 17.9. So I got, yeah, 17.9. That's what I got. Yeah. So this basically, that's the same number that we have here. Yeah. 17.9. Okay. So simple stuff. Okay, let's see how we are doing in time. I think we are doing good in time. Uh, uh, I'm keeping it like short. So this is like your practice problem. Let me show you your practice problem. So basically like here, like let's just recap what we did here. So what we did here, first we were able to, by knowing the pertaining variables, we were able to derive a relationship, we were able to derive this pi terms, like non-dimensional parameters. And from these non-dimensional parameters, if we can assume, like if we can achieve similarity, then we can use the model to do some prediction about the prototype. So what we did here is that we make sure that the model has kinematic similarity, it has geometric similarity, and now we can make prediction like when the drag force in this model is equal to 16.1, the drag force in the prototype will be equal 17.9. That's how you scale it. Yeah, so you see it scales by a factor. So let's do something similar, and let's do an application from like environmental engineering or like water resources engineering or whatever. Yeah. So here, like we have like a prototype gate valve. So this is like a gate valve. This is called like a gate valve. So and these valve usually have like head drops. So the hydraulic head will drop, which will control the flow in a conduit conveying like hazard fluids. Is used to study with a physical model with water. So basically, we have like a hazardous fluid big valve that regulates some hazardous fluid, but we don't want to study like use hazardous fluid like in the lab. We just want to replace the fluid, this fluid with water. Is this a problem? No. I mean, they have different density and viscosity. That's fine because we know our scaling rules, yeah, and we know our dimensionless parameters, so it doesn't matter, yeah. So from our understanding of the system, the pressure drop due to valve is expected to depend upon valve gate opening. So like how opening, like how this gate is open. So I'm giving you here the pertaining parameters because you might not understand this system, you might not know the pertaining parameters. So I'm giving you the pertaining parameter. So the pressure drop that could be like due to the gate opening. So here the gate is fully open, the valve overall depth, like this distance, like the distance from here to here. So you have like this distance, but it could be fully closed or it could be fully opened or it could be half open or it be whatever, yeah. So, but that is like another parameter. And of course, the velocity, the fluid density, and fluid viscosity. You always have like these, like most fluid problems, fluid mechanics problem, you'll have velocity, you'll have density, and you have viscosity, yeah, because that's how you define like your fluid. And the kinematics of your fluid velocity will define the kinematics of your fluid. Yeah. So perform dimensional analysis to obtain the relevant non-dimensional group to scale the model to the prototype. So here, like just without knowing anything, by just looking at this, like how many variables do we have? So here we have the pressure drop, that's like variable number one. We have H, that's variable number 2. We have D, that's variable number 3. We have V, that's variable number 4. Density, 5. And this guy, 6. So we have 6 variables. How many dimension we have? We only have 3 dimension, like that is like length, mass, and time. Then how many non-dimensional parameters are we expecting to get? So we are expecting to get like 3 non-dimensional parameter. Like we are expecting to get like pi 1, pi 2, and pi 3. So the final thing that we are expecting is like pi 1, our dependent variable, would be a function of like pi 2 and like pi 3, which we don't know. Again, how did we know this? Because we have like 3 dimension, we have 6 parameters. This will give us 3 non-dimensional parameter. In the previous problem, we only had like 5 parameters, 3 dimension, and that's why we only had pi 1 and pi 2. But now we here have an extra parameter. If we have 7 parameters, then we will have pi 1, pi 2, pi 3, and pi 4, and so on and so forth. Yeah. So I'm telling you here, perform non-dimensional analysis to obtain the relevant non-dimensional group, non-dimensional parameter to scale the model to the prototype. And then here I'm asking you to solve some problem, like similar to what we did before. So like I will give you the that is density and viscosity of this fluid. That's the density and viscosity of water, for example. I'm giving you like for a particular opening when velocity hazard flows in the prototype is like I'm giving you the velocity, then I'm telling you what is the velocity of the other one to to ensure similarity. So this is similar to the previous problem, and then I'm giving you what is the ratio of the quantity of flow prototype and model. Like I'm asking you about like the quantity of flow. You know velocity, you know the areas, and you can calculate like Q. Yeah. And then find the pressure drop in the prototype if it is kilopascal in the model. Yeah. So I'm just asking you pressure drop in the prototype versus in the model. Yeah. So I mean, this is just like part two. Like you do this after you find like your non-dimensional group. So I mean, I don't. You should be able to solve this on your own, basically. So here we know this is our independent variable. Yeah, this is our independent variable, and sorry, this is a dependent variable, and these are our five independent variable, like the opening, the diameter of the valve, the velocity, the this. So I will not show you the solution because I want you to do it on your own. Like you identify the repeating variables and remember like how to do the repeating variables. So your repeating variable should have like the length, the uh, time, and the mass. Yeah. So this to get like geometric, kinematic, and dynamic. Yeah. So basically like that is like so for example, like for the lens, for example, like we can choose any of these parameter, like you can choose overall depth, for example. Yeah, that could be like to ensure geometric. Kinematic or time dependent, that of course would be the velocity. Uh, Dynamic or something that's mass dependent, we can choose as we did before, like the density. Yeah. So I will not, I will stop here. I mean, you can just follow like the similar steps that we showed in like, not in this video, like in the previous video to find like your non-dimensional parameter. So like I will, and again, the answer, like if you check try to solve it in your own because that's how you will learn. And if you cannot solve it or check like your answer with the answer in the class notes. So this is basically like step 3. Step 4, that's like where you find like, and then here we ended up with pi 1, pi 2, and pi 3. And then once we have, so here we end up with like a relationship between our dependent variable and like all our independent variables. And then once we do this, we can just do scaling similar to what we did before. So pi 1 like scale was pi 1, pi 2 scale was pi 2, pi 3 scale was pi 3, and then you can do like this different calculation. So like the final answer is here. I mean, I'm not going to do this. That's like your practice problem. So you should be able to practice and do this on your own. And then that's your homework problem. It's basically I'm giving you like this same problem again. So the homework is really trivial. Like so that is like a trivial homework because what I'm doing, I'm just giving you the same problem again. So basically I'm telling you do dimensional analysis, and then I'm giving you like after you do dimensional analysis, you get pi 1, pi 2, pi 3. Like use them to answer these questions. Yeah. So model type similarity to ensure similarity like determines the corresponding velocity similar to what we did in the exercise problem and what you did in the practice problem. Flow rate scaling like scale Q and scale like your dependent variable, which is pressure. Yeah. So I mean the homework really is trivial. I mean it's trivial if you watch the video. Yeah. If you didn't watch the video, I mean you're not going to be able to solve it. Yeah. And you'll say, oh, that's very difficult, but that's because you didn't watch the video. Yeah. Uh, uh, okay, so I will keep it. Remember, I have to keep everything less than 2.5 hours. So I'm keeping it less than 2.5 hours. I will stop here, and that's the end of this module. By the end of the module, what do you do? Like, do you remember what do you do at the end of the module? So you finish the module. You just go to Canvas. Like you finish the module. I mean, you go to Canvas. And what do you do in Canvas? Like you do the homework, of course, and then you do the participation log. You do the module survey, and then you're done, and then you move to the next module. Okay, so see you in next module, which is about calculus, which is very interesting module, much more interesting than this stuff. But this stuff are fun also, yeah. I hope you find them fun. Okay, bye bye.